So very good evening to all of you, and good morning and good afternoon to all of you as well. So we are going to start the fourth session of this conference. So the next speaker is Dr. Muhammad Kawaja Nasruddin. So Dr. Muhammad Kawaja Nasruddin currently holds an adjunct professor at EPFL, Switzerland, in the group for molecular engineering of functional materials for photovoltaic and LED applications. So Professor Muhammad received his PhD in inorganic chemistry from Osmania University, India. His current research focuses on dye-sensitized solar cell, perovskite solar cell, CO2 reduction, and hydrogen production. And he is one of the renowned person in the field of perovskite and dye-sensitized solar cell. And to his credit, he has published more than 725 peer-reviewed papers, 10 book chapters, and he is the inventor and co-inventor of more than 90 patents. And he has been named Thomson Reuters highly cited researcher and has been identified by the Times of Higher Education as the top 10 researchers in the world working on high-impact perovskite materials and devices. He appeared in ISI listing of most cited chemists, and he has more than 0.1 million citations with an H index of more than 145. So we welcome Dr. Muhammad Kawaja to deliver his talk on perovskite solar cell, a new paradigm in the energy sector. So we welcome you, sir.
Can you see my screen?
Yeah, it's
okay. First of all, thank you for this kind invitation, and thank you, Chairperson, for your kind introduction, which I really appreciated, and Professor Grace for this kind invitation to present our work in this conference. So the title of my talk is Perovskite Solar Cells, a New Paradigm in the Energy Sector. As you will see why I call this as a new paradigm in the energy sector. So I'm working at EPFL. I also have affiliations, 3 other universities, Korea University, University of Brunei, and King Abdulaziz University. Here is my email address. So if you have any queries, please send me your queries and try to answer you as soon as possible. Now I take just a second slide, which is showing our campus. This is our campus. We have a very nice lake going from Geneva to Montreux. This campus, this is our Congress Center. I'm hosting the IPS 23. If you happen to have a chance, please come and attend this meeting. So this is our Congress Center. Now come back to the topic, perovskite solar cells, and we are putting in context with the silicon solar cells. Silicon solar cells efficiency, as you know, all 26%. And the perovskite solar cells, which last year has been certified at 25.5. In our group, we are getting 25% efficiency certified. And this efficiency data I am reporting from Korea, that's at 25.5. So this is at present the world record. Now coming back to if you look at the design configuration, what is the difference between the silicon solar cells and perovskite solar cells is shown here as contrast. On the right side, the perovskite material is sandwiched between the 2 charge transport layers. One hole transporting material, and the other one is electron transport material. All these 3 layers are solution process and sintered at low temperature, 120 degrees temperature. Compared with the silicon solar cells, and this is a very complicated energy intensive process where we have to take the metallic silica and then crystallize into monocrystalline ingots. And this is a very highly energy intensive process ranging with 1400 degrees temperature. Besides that, the other disadvantage of silicon solar cells is when we are bringing this metallic silica, so you are bringing this material from the silicon dioxide. So naturally, we are producing a lot of carbon dioxide as a byproduct. But however, the efficiencies are very similar. And you will see what are the differences as we go on in my presentation. So what is perovskite actually? If you look at the perovskite materials, They are very simple, a salt type of material, having a typical formula of ABX3. A is a monocation, B is a dication. Under monocation, it can be inorganic or it can be organic. And the dications are metal, that's a lead 2 plus or tin 2 plus. But the lead 2 plus is the efficient one because of the heavy atom effect. And the halides can be the bromides, or chlorides, iodides. But if you look at the band gap of these materials, iodide has the smallest band gap compared to the bromide, and the bromide has the smallest band gap compared to the chloride. You can have an opportunity to tune this band gap, you will see in my presentation. So what is the beauty of these materials? I highlighted 3 points. They absorb very strongly in the whole visible region, and you can tune the band gap of these materials either by changing the A cation or by changing the halide. And this way you can have the properties the way you want to tune these materials. Another striking important property of this material is exciton dissociation energy, which is very small. What does it mean? When you have this material, shine the light, the carriers are instantaneously getting separated and collected at the charges. Don't form the exciton in the process. And this is the main one of the reasons why the efficiencies of these solar cells are so high. Now, as I mentioned in the first point, that it absorbs all the visible light as shown here. It absorbs from 400 to 820 nanometers. And wherever you excite, we have a very nice emission maxima coming around 790 nanometers. And this material has a very nice characteristic features similar to gallium arsenide. So the gallium arsenide, if you look at this one, the blue line is the gallium arsenide, very sharp onset. And similarly, methyl ammonium lead iodide has a very sharp onset. This shows the very low trap state densities in this material. Now, coming back to the device configuration, on the left side is a cartoon, on the right side is a cross-sectional image of our solar cell. So what we are having is a conducting glass deposited with a compact layer of TiO2, followed by, can you see my cursor? Can you see the laser pointer?
Yes, yes, yes.
Yes. Okay, so we deposit a compact layer of TiO2, then followed by mesoporous layer of TiO2 and tin oxide. It's a bilayer configuration. Then we deposit perovskite in the range of 600 to 700 nanometers thickness. This is perovskite. So the compositional engineering of this perovskite is very important to have the crystallinity of these materials. Now, if you look at the sum of these crystals, they are blocks contacting between the ETL layer, that's a TiO2. On the top, we have a hole transporting material. This is a hole transporting material on top of the perovskite, followed by we have a contact. So this is a configuration. So such a simple configuration gives you 25% efficiency of the perovskite solar cells. Now, the beauty here is now we can go on modifying either electron transport materials, optimize further to enhance the stability, and compositionally engineer the perovskite to increase the stability as well. And we have a hole transporting materials which are very efficient, that gives you very high VOC. So with this material, we in the lab, we get 24.33% efficiency, which is certified at Newport very recently. This work is still not published, so we have certified the lab data at Newport in an independent laboratory. You can also make a mini modules of this size because of the limited the facilities what we are having. So the 6.5 by 7 centimeters, that's a close to 30 square centimeters area, that gives you 21% power conversion efficiency. If you look at the silicon wafers, they are in the range of 18 to 20, depending on the manufacturers. So we are very close to silicon solar cells, but the beauty here is you can change the color of these materials. That's not the case with the silicon solar cells. By changing either halide or cation, you fine tune by changing the cation, and grossly tune the color of this material by changing the halide. Other added advantage is you can also fabricate this perovskite solar cell on plastic substrates as shown here. So this gives you the opportunity to integrate these materials into the buildings so that the buildings can be energy efficient. What's the problem then? Look at the perovskite solar cell efficiency, 25%, which we have certified and the whole world is working on it. Silicon solar cell efficiency, 26. But what is missing in perovskite solar cells compared to silicon solar cells? The stability is the biggest problem. Silicon solar cells, you will get the guarantee of 25 years without any problem, but the stability of the perovskite solar cells are not there. So we have to work to improve the stability of these materials, and that's what my talk is today. So the perovskite solar cell, how we can improve the stability of these materials? The one aspect we are taking is, can we engineer the interface to enhance the stability? Point number one. Second, can we enhance the stability of these materials by compositionally changing this material? The third point is charge transport materials. The perovskite material is encapsulated between the electron transport layer and the whole transporting material. So change these interfaces or change these materials to enhance the stability of these materials. So that's what my talk is. So now I come back to the perovskites. Within the perovskites, there is a subclass of materials, that's the low dimensional perovskite, which we will discuss on this slide. So what you see on the left side, this is the perovskite material. Imagine the lead as an octahedral complex. Iodides are corner shade in all these the complexes and forming a three-dimensional network. And then the charge compensation is carried out by inserting the cation in the cavity. Let's say this is a three-dimensional perovskite. Now, what happens if your cation size is bigger than the cavity? For example, we are using cesium as an inorganic cation or methylammonium as an inorganic cation. So this cation easily fit into this cavity to form this in a three-dimensional perovskite material. Now, tomorrow you change the cation from methylammonium to phenylammonium, phenylethylammonium, as shown here, this cation. And this cation size is so big, this will not fit into the cavity, so that the layers are slit into one-dimensional perovskites. So it's now you have a great opportunity to tune the dimensionality by combining the smaller cation and the bigger cations. Now the composition you can engineer in such a way that the number of the n layer equals, let's say, three-dimensional perovskites, and the number of the two layers perovskites or three-layer perovskites, you can control the whole composition. Now look at the properties of these materials. So now discuss about the UV visible absorption spectra of the three-dimensional perovskite. That's shown here, the dashed line on the bottom right side. So it absorbs up to 820 nanometers. So the drawback of this three-dimensional perovskite is the stability, and stability is not very good. So what we have to do is we change the dimensionality and we go for the two-dimensional materials using some of these cations shown highlighted here. But you can immediately find out that the two-dimensional perovskite absorbs only a small portion of the visible light. Thereby, the efficiency of these two-dimensional perovskite materials can be significantly lower. Think of combining three-dimensional perovskite, which absorbs all the visible light, and combining with the two-dimensional perovskite, which are not absorbing, but which is providing enhanced stability. That's what you will see in my next slide. Here is the data shown. So we are taking two configurations. One, pure perovskite with cesium, formidinium, methylammonium, lead iodide, bromide perovskite. This is a normal configuration. It acts as like a reference sample. And now we deposited on this sample a layered perovskite. That's a two-dimensional perovskite. So the UV visible spectral data are shown here on the right side. The green line is a pure two-dimensional perovskite involving phenylethylamine as a cation. As you can see, it's a very narrow absorption. A very small portion of the visible light is being absorbed. The black line is a pure three-dimensional perovskite. Now, if we deposit the two-dimensional perovskite on the top of three-dimensional perovskite, the spectral properties are shown. That's a red line. Now, if you look at the cell by naked eye, without any two-dimensional perovskite, you don't see any color. However, the presence of two-dimensional perovskite clearly shows a very green color because this two-dimensional perovskites absorbs and they are highly luminescent. This you can see by naked eye. So look at XRD on the left side. The red curve shows the pure two-dimensional perovskite. The green one is a pure two-dimensional perovskite. Just focus on this fingerprinting. That's a 2 theta around 5 is pure two-dimensional perovskite. On the bottom black line, around 14, this is a fingerprinting of XRDP to the 2 theta 14 for the three-dimensional perovskites. By combining three-dimensional perovskite and two-dimensional perovskite, you can see the central the graph, which is you have a two-dimensional perovskite presence as well as three-dimensional perovskite fingerprinting. The other way of characterizing these materials are shown here. So now we take the two cells, one as the reference, that's a cesium, formidinium, methyl, lead iodide, and bromide perovskite. That's a reference sample. We excite at 450 nanometers. From the top side, we see only one emission coming from the three-dimensional perovskite. However, if we deposit the two-dimensional perovskite on the top of three-dimensional perovskite, now we excite at 450 nanometers. You can see the very sharp emission coming from the two-dimensional perovskite, which is around 520 nanometers, followed by the laser is hitting also the three-dimensional perovskite when we have a two-dimensional perovskite deposited on top of three-dimensional perovskite. That gives you a similar peak here. If we excite from the bottom side, both the reference sample as well as two-dimensional perovskite deposited, the perovskite shows the same emission peak, overlapping one on the top. What does it tell you? So the two-dimensional perovskite deposited on the top remains as a layered perovskite on top of three-dimensional perovskite without penetrating into the three-dimensional perovskite. Now, if you look at the UPS data, that's a energy level diagram. So this is our perovskite, the HOMO level and the LUMO level of the perovskite. And after measuring the UPS data, you can build the energy level scheme of the two-dimensional perovskite, which is shown here, this yellow line, and the spirometered gold-transconium material on the other side. So what is happening here is when you shine the light within the perovskite, you create charges, and the positive charges are extracted through the two-dimensional perovskite because the HOMO level of the perovskite, three-dimensional perovskite, and the two-dimensional perovskite are well aligned. However, the LUMO level of the two-dimensional perovskite is significantly above the three-dimensional perovskite. So the electrons which are generated within this perovskite, they come to this site and they turn away towards the Atl layer. On the contrary, the positive charges are extremely efficiently extracted into the whole transporting material. So what is happening at this interface? Just imagine it for 1 second that we are effectively reducing the recombination at this interface by avoiding electrons, by pushing the electrons towards Atl layer, by pushing the positive charges toward the whole transporting materials. How do we know that this is happening? Let's take the IV characteristics of these materials. So take the reference sample, which has a VOC of 1.09. This is the open circuit potential of the reference sample. After depositing a two-dimensional perovskite, the open circuit potential has increased to 1.14. So even though this number looks too small for you, but this is a significant number for us to tell that the recombination has significantly reduced. So the optimized efficiency is close to 21% efficiency using this three-dimensional perovskite and two-dimensional perovskite. Now, the beauty of depositing the two-dimensional perovskite on the three-dimensional perovskite is shown here. So the open lines are under argon atmosphere measured the stability, long-term stability of these perovskite solar cells up to 800 hours. And that the solid lines are encapsulated but measured under outside conditions, atmosphere conditions. However, under similar conditions, that's a reference sample measured under argon atmosphere, that's open circles, and measured under normal air conditions with encapsulated, the efficiency, the stability is decreasing significantly compared to the layer by layer deposition. So the take-home message is that's a layer by layer deposition, enhances the perovskite stability significantly. Is it the only cation which is doing? So we have taken another two cations as an example. This is a fluorophenylethyl and pentafluorobenzylamine. So these are the two new cations which we have synthesized and worked with these two-dimensional perovskites. Look at the absorption spectral properties. The fluorophenylethylamine is slightly redshifted, close to 550 nanometers, whereas the pentafluorobenzylamine cation gives the two-dimensional perovskite around 490 nanometers absorption maximum. And similarly, we deposited on top of the three-dimensional perovskite. The data are shown here. Now, without going into the characterization details as before, but let's go directly to the PV data. So as a reference sample, pure three-dimensional perovskite, focus on the VOC, that's a 1.09 volts, that's a black line. Now, after depositing the fluorobenzylamine as a two-dimensional perovskite cation, now if you look at the VOC, increased from 1.09 to 1.13, as that's a blue color, that's an IV characteristic is shown here. Now going from the fluoro to pentafluorobenzylamine, the VOC has increased from 1.09 to 1.15. So this shows the beauty of tuning the two-dimensional perovskite cations. And the reason why we have taken the pentafluoro is they are hydrophobic. So perovskites are hydrophilic material. So you have two functionalities incorporated into this material. One, surface passivation. The second, its hydrophobicity protects your perovskite. Now, if you look at the stability data measured over 1,000 hours with the pentafluorobenzylamine, the stability is greatly enhanced. You can see the details of this work in this article. Now I come very quickly, the compositional engineering of perovskite layers. So look at the methylammonium, formidinium, and guanidinium. So these are the three cations I have taken example. So this is a Goldsmith tolerance factor, where the cation size is within this range, you form the cubic three-dimensional perovskite zone. If the cation size is too big, it will not form the perovskite, and too small, it will not form the perovskite. So guanidinium, having a 3 NH2 groups, the purpose of selecting this one is to enhance the hydrogen bondings, therefore increase the stability of the composition. However, because of the larger size, it doesn't fit into the tolerance factor. It will not form the perovskite. But however, what we did was combining the smaller cations, 75%, bigger cations 25%, as shown in this cubic unit. So you have a 75% of the smaller cation and just 25% of the bigger cation. They adjust into the cubic cell, and the cell configuration is shown here. Now, if you look at the data, the black line, the stability is very important to show. The black line is the normal perovskite without guanidinium as an additive, which is decreasing over the period of 1,100 hours. However, if we have a 25% of this guanidinium and 75% of methylammonium, that's a red line. That red line, the efficiency remained constant after initial decrease of the performance. So now I take another two examples just to conclude. So we have another composition, which is a ionic liquid. Here the purpose is twofold. One, fluorinated substitutions creates the hydrophobicity, and the double bonds, they will polymerize. Now, without going into the detailed configuration of these solar cells, now if you have this ionic liquid, if we use as a reference sample, if you see the reference sample, this produces lead iodide, showing the decomposition pattern. However, if you have 1%, the decomposition is decreasing significantly. If you have a 2%, it further decreases 4%. There is no formation of lead iodide, showing the stability of these materials. So here is the blown up the data here shown here. So this is clearly shows that the no formation of lead iodide shows the material is quite stable. And also, when we put this solar cells outside, with 1% of this ionic liquid inside the perovskite composition, 2 months under ambient air with 50% humidity, the front side and back side under similar conditions, you can see the reference sample, which is decolorizing immediately, highlighting the performance characteristics of this 1% ionic liquid into the bulk perovskite material. Now the question is, what is this ionic liquid doing? How it is forming and why it is protecting? Look at the XPS analysis. So when we have the XPS fluorine binding energy, which is shown here, this is fluorine binding energy of the materials with the 0, 1% and 4%. Now we took the perovskite 1 grain with focused ion beam. You can treat the surface from the top to bottom, and you can see from the 0 nanometers, we have a significant amount of the fluorine and up to 25 nanometers. But the moment we go up to 50 nanometers, the fluorine is not there. So let me just explain you what is happening. When we have this 1% of ionic liquid in the perovskite, and because of the solvent, the ionic liquid is floating on top of the perovskite. And when the perovskite is forming the crystals and is forming a shell around the perovskite grains, as shown from this data, the stability is significantly enhanced compared to without ionic liquid. The second ionic liquid, we how much time I have? Hello? Hello?
Oh, yeah. You have.
How much time I have?
So you have another 10 minutes.
Okay.
10 to 15 minutes.
Okay, thank you. So I have another ionic liquid which I have to show here. This is the ionic liquid with the double bonds on the both sides. This is a vinyl ionic liquid. So when we use this ionic liquid with the standard perovskite, that's a methyl ammonium lead iodide, which is extremely unstable. But however, you can make these perovskite solar cells outside the normal as a reference sample, the efficiency is only 15%. That corresponds to this block IV characteristics. If we use this 1% ionic liquid, the efficiency increases from 15 to 17%, which is corresponding to the red IV characteristics. So the EQE data is shown on the right side. This is the composition based on methyl ammonium lead iodide. Now, if you go to the advanced composition based on formaldinium methyl ammonium lead iodide, this is the reference sample. The black line IV characteristic shows the power conversion efficiency close to 17%. By adding this ionic liquid, small additive, and that increases the efficiency, that's a 2% of ionic liquid, increases efficiency from 17% to 19%. So this is an enhancement in the power conversion efficiency by using this ionic liquid. But the beauty here is we made another ionic liquid, very similar, but except you don't have the double bonds. On the left side ionic liquid, you have a double bonds, which immediately gets polymerized at high temperature, at 150 degrees temperature. If you don't have a double bonds, this will not polymerize, but it's a similar ionic liquid. Now, if you look at the stability data with ionic liquid, this remains over 90% stable compared to as a reference sample. So I come very quickly on the charge transport materials. So as we have seen, we are building the perovskite solar cells encapsulating between the hole transport material and electron transport material. So we discussed in detail on the perovskite, the composition. Now we go to the hole transport material, which is on the top of the perovskite. So far, the best working hole transport material is spirovometide, which has all the following issues: stability, price, and purity. So these are the issues with this material. The reason why this spiro has issues are they are not highly mobile conductive. So we have to dope with the dopants. One of the dopant is cobalt-3 complex, shown on the left side, lithium TFSI, and tertiary butyl pyridine. By doping with these agents, what you do is you oxidize intrinsic hole transporting materials, and by oxidizing the intrinsic hole transporting material, you increase the mobility. That enhances your hygroscopicity, as shown here. So look at the spirometad without any dopants, and with the dopants, the contact angle decreasing significantly. Not only that one, so we have a pyridine, which is a strong base, which nucleophilically attacks on one of the groups of the whole transporting material. So to avoid all this, we have developed a new whole transporting materials based on the thiophene, is shown here, and this was published in 2016. The efficiency is not very high, around 20%, but the beauty here is that it binds to the perovskite, as shown this DFT calculations. So if you look at the spirometad, the interaction is very weak through the oxygen and the perovskite. In the case of new whole transporting material, you have a thiophenes which interact strongly with the perovskites, so precipitating the vacant sites, and also it interacts with the methoxy groups as similar to the spirometad. So this is the lesson which we have learned, and then we went back and then redesigned the molecules to have a dopant-free whole transporting materials. So there are three functionalities in this design concept. So we have a disc type of core molecule, which is attached with the three arms with the sulfur groups, with the thiophene groups as before. So the purpose here is to have these cores to stack one on the top, so that the whole transporting material should work without dopants. So is cartoon is shown here, how the whole transporting materials, they stack one on the top, forming columnar shaped whole transporting material on top of the perovskite material. With one thiophene, the efficiency is not very high. With the two thiophenes, the efficiency without any dopants is around 15%. With the three thiophenes, there's a KR321, where this group, the red entry, is around 19% efficiency. This is a pristine molecule synthesized and directly absorbed onto the surface. And on the contrary, if you look at the spiro, this is with the dopants, and the efficiencies are comparable. So here we have a huge success to demonstrate the dopant-free whole transport materials as efficient as with the doped spirometad. And then followed by, we have made another new class of materials, which last year we published. These are the three new class of materials, and they also show very nice efficiencies without dopants, by the way. All these without dopant whole transport materials are very efficient and comparable to spirometers as shown here. So C1B1, that's a 15% efficiency. C1B2, that's a 15.3% efficiency. C1B3, that's a 17.5. With these all are without dopants. With the spirometad as a dopant, we have a 18% efficiency. Similarly, I go very quickly on the Atl layers. So the Atl layer, we were using the compact TiO2 followed by TiO2 and then passivated tin oxide. And here we have showed the efficiencies in the range of 22% efficiency, and which was certified at Newport again. This was in 2019. Now we have a new configuration, which is shown here. And this appeared very recently, it's online. So if you have a pure TiO2, the perovskite solar cell is degrading. On the contrary, if we have a pure tin oxide, and the material interface seems to be extremely stable, performance up to 1000 hours. By combining tin oxide followed by TiO2, we can see that data is shown here. This is also extremely stable. So the take-home message from the Atl modifications is we do need a tin oxide perovskite interface. The moment we have a TiO2 and perovskite interface, the perovskite is not very stable. So with that one, I would like to conclude that I have shown you the beauty of depositing the two-dimensional perovskite on top of three-dimensional perovskite to enhance the stability. I showed you the guanidinium as a new cation to enhance the perovskite stability of the unstable methylammonium lead iodide perovskite. Hydrophobic ionic liquids, I have taken two examples to show how to enhance the stability. We have developed new dopant-free hole transport materials that shows the comparable efficiency to spirometry. So this is my PhD students and postdocs and international collaborators, which I would like to thank them for their excellent contributions. And here we have a funding agencies which generously supported our research. And thank you for your attention. I will be happy to answer your questions. Thank you.
So thank you, Professor Nasruddin, for your wonderful talk and shedding some light on the stability of perovskite. So I have some couple of questions.
Yes.
So we have shown three different way of improving stability through engineering. So out of these three, interface, compositional, and charge transport, which one would you prefer the best one? Or it's a combination of
it's a combination of the three is required to have a enhanced stability, because till today, last 10 years, the whole world is struggling and working on enhancing the stability of these materials. Till today, we don't have any success. And here we have a light at the end of tunnel where we show stable performance by compositional engineering as well as the charge transport material modifications and interface modification.
And
are required.
Okay, thank you. Regarding this interfacial engineering, you have used 2D materials on top of 3D perovskite. It's something like a layer by 3D, 2D, and 3D and 2D, or it's something like you have 3D perovskite and then you coated 2D perovskite materials on top of 3D.
Yeah, so at present, all the data which I have showed you is 3D and 2D, but the going to the 2D followed by 3D and 2D can be an interesting concept which we are working. Okay. So far, we haven't done that one, but this can be a very interesting concept. 2D, 3D followed by 2D, where the three-dimensional perovskite, which is unstable, you encapsulate, zip under between the two-dimensional perovskites.
What's the actual physical mechanism behind these 2D encapsulated 3D perovskite materials? You said something about this blocking of electrons reaching from 3D to 2D, but in terms of stability, this moisture and what is called water content, that will affect actually whether it will block this moisture content.
That's true. It's a blocking the moisture content. Okay. And if you see the choice of the cations, we are having hydrophobicity enhanced cations. That's the reason why the stability is increasing.
Okay. Whether band gap also plays an important role, whether we can tune the band gap of this 2D material based perovskite.
Yes, the band gap can, this way, it's a very interesting question actually. So the band gap tuning is very interesting topic. Here we have to really redesign the cations, synthesize using with the DFT help to identify the band alignment, which is very important. And this is so far not many groups have explored. Only one or two are working towards this recently, but this is going to be a very interesting topic in future.
One more questions regarding this stability test. So just for curiosity, how do you test this one for 1000 hours? Whether we need to.
Yes, we have a special chamber with the LED source. The intensity of this LED source is close to 1 sun, and this LED source provides 60 degrees temperature. So we keep our cells in this box under argon atmosphere. If we don't encapsulate, if we encapsulate, we don't put the argon atmosphere. So it's a LED source. The question also, this is question also quite coming from the expert. The reason why we are using LED is still our materials are not that stable under UV radiation. So we are not using full sun intensity. We are using only UV light. LED source.
Oh, okay. So one general question regarding this toxicity of lead-based perovskite. So what is your opinion whether, because now this scientific community of perovskite solar cell, they are trying to market this perovskite. But one more concern is this toxicity of lead actually. So what is your opinion on the toxicity of lead? Because in some paper they say that the toxicity of lead is in acceptable limit, but in many papers they say so toxicity is one of the important concern when we just go for these practical applications.
Surely I'm not underestimating the toxicity issues of the lead. So this is the known factor. Lead is a toxic material, there's no doubt about it. But if we do in isolated areas like solar fields using perovskites, where we can use this cheap electricity to produce hydrogen, that can be a very nice combination of cheap electricity and producing the hydrogen from using water. So this combination, I'm not recommending this to install immediately on the buildings, but this can be a very nice initial applications to produce hydrogen using in remote areas till the acceptable level of the community accepts the lead.
One last question. So based on your expertise, how long would it take actually to commercialize this perovskite based solar cell just to compete with the silicon based solar cell?
I think it needs at least another 5 years, because since I'm aware of the companies who are working on these technologies, particularly silicon solar cell companies who wants to put onto the perovskite on top of silicon solar cells to increase the efficiency of silicon solar cells. So this, once if they reach 30% efficiency, I think this product is really has a high value with the low LCOE and the high efficiencies. But it needs some more time. Right now, we are in the right direction with the stability and efficiencies.
So one more question from participant: why this inverse perovskite structure is not as familiar as normal perovskite structure?
Yeah. Okay. So in the normal perovskites, we are using inorganic electron transport materials which are extremely stable. And in the inverted perovskite solar cells, we will be using either PCBM or C60 as electron transport material, which are interesting materials, but the long-term stability is still questionable there. So that's the reason why the many groups are still focusing on the NIP configuration, where you use inorganic metal oxide like TiO2 and tin oxide as the Atl layer.
May I ask one more question?
Yes, please, go ahead.
So, what is your opinion on this flexible based perovskite and rigid based perovskite?
Yeah,
on
yes, the flexible substrates are quite interesting for applications ranging from space to drone applications. The efficiencies are at present, they're not as high as the glass substrate based ones. Glass substrate based ones are 25. With the flexible substrates, we are hardly reaching around 12% efficiency. So the moment we reach high efficiencies with the flexible substrates, the applications also again enormous on with using these flexible substrates, because they are lightweight, can be used for the space applications and various other applications, military applications as well.
So thank you very much, Professor M.K. Nasruddin.
Thank you, Professor Nasruddin, again for this interesting talk on perovskite solar cells. Thank you for accepting our invitation. On behalf of VAT, thank you, Dr. Nasruddin. Thank you so much.
Thank you. Thank you for your kind invitation.
Yeah,
all the best.
Pleasure.
Bye.
Thank you. Thank you.
Bye.
Yeah, bye. Hi, Dr. John. You joined. Yeah. Yeah. Dr. John.
Can I start? Yep, I'm ready.
Yes. Yes, we can get started.
Sure. Let me start.
Yeah, before that, we'll introduce you. Let me request Professor Raja to introduce.
Oh.
So good morning, Dr. John Wong Hong, and good evening, all of you. So it's my great pleasure and privilege to welcome Dr. John Wong Hong from MIT, United States of America. So Dr. John Wong Hong is a research scientist at MIT, Laser Biomedical Research Center. After receiving PhD from Post-Tech, South Korea, he joined Wellman Center for Photomedicine as a research fellow. He has been working on biomedical spectroscopy projects, including spectroscopic cancer diagnosis, non-invasive glucose monitoring, intraneedle optical sensor, and so on. He is also interested in commercializing, and also he is a co-founder of a medical device startup company called Medicite. So with no further delay, I would like to welcome Dr. John Wong Hong for delivering his talk on non-invasive glucose monitoring using NIR Raman Spectroscopy. So thank you very much.
Thank you, Chairman, for kind introduction. Let me share my screen. Do you see the screen?
Yeah, we are able to see.
Here. Yeah. Thank you, everyone. So hello, my name is Jeonung Kang at MIT Laser Biomedical Research Center. Today, I will introduce our non-invasive glucose monitoring sensor using NIR Raman spectroscopy. Before starting, I'd like to thank my boss, Dr. Ramachandra Rao Dasari, who invited me to this exciting journey of non-invasive glucose monitoring. So MIT Laser Biomedical Research Center is a part of Harrison Spectroscopy Laboratory. Harrison Spectroscopy Laboratory is one of the oldest laboratory in MIT. So it started from 1931 by Professor George Harrison, and the second director was Richard Roth, and third director, under the supervision of third director Professor Michael Felt, actually laboratory started working on application of optics and spectroscopy to tackle biomedical problems. And with Michael Felt and Dr. Ramachandra Rao Dasari, so we started Laser Biomedical Center at 1985. So some of the well-known people in the laboratory include Professor Charles Towns, who invented the laser, and also Professor Ali Jaban, who invented the first gas laser. It's a helium-neon laser. So since 1931, Harrison Spectroscopy Laboratory has been working on optics and spectroscopy science. And since 1985, we have been working on tackling biomedical problems using optics and spectroscopy techniques. Since then, we were supported by NIH. So it's one of the oldest biophotonics laboratory in the USA. So diabetes is a worldwide problem as people are consuming more food and especially more sugar. At 2007, 170 million diabetic population was there worldwide, and this number is expected to increase up to 300 million at 2025. So in the US, it is more serious. So among adult population, about 13% of the total population is diabetic, and about 3% of the population is diabetic but undiagnosed. So among senior population, it's almost one person out of 4 people, so heavily affected by diabetes, and it costs a lot of money, and also it's a 7th leading cause of cancer. And diabetes is a major cause of blindness, kidney failure, heart attack, and so many other problems. So everybody understands that you need to tightly monitor your blood sugar levels in order to control diabetes. So there are currently 3 established methods. First one is a clinical blood analyzer. If you go to hospital, then they take out blood out of mostly from your arm, about 3 ml or 5 ml. And they put it into this machine and it gives you the blood sugar levels. This is the clinical gold standard, extremely accurate, but you cannot use it at home because of the price and the size and very uncomfortable to use it every day. And many people are using finger stick device. You prick your fingertip and you use a strip here and you put your blood into there and it is reading the blood sugar levels. So it is easy to use, but still many people, because still you need to take out a drop of blood out of your fingertip. If you do it several times a day, it is annoying and a little bit painful. So people do not like it. And more recently, people started using minimally invasive sensor, like a Abbott, Dexcom, or like a Medtronic. They have this kind of sensor. This small wire is going under your body. It can be your belly or it can be your forearm. And it is continuously reading your blood glucose levels and send the signal to either like a cell phones or computer using the Bluetooth technology. So this is actually, once you embed the sensor under your skin, it can read your blood sugar levels for up to 1 to 2 weeks, but still it is kind of invasive and it can cause inflammation problems. And it also requires a calibration frequently. So optical sensor is a completely non-invasive technique. Has been a promising technique to monitor blood glucose levels. So there are two types of the techniques, if you categorize them. First one is the indirect technique. Indirect technique is you are measuring glucose levels from the other indicator. For example, optical coherence tomography or tissue refractometry. What it reads is the change of the refractive index in your tissue. So typically, when you have a high concentration of the glucose, you can imagine that if you dissolve sugar in the water, in the glass, then you can see it has a different refractive index. It's like that. From measuring the refractive index changes of the tissue, you can extract the blood glucose level changes in your tissue. So since it's an indirect technique, it can be implemented as a low-cost device. But the issue is that the tissue refractive index changes are not always coming from the blood glucose concentration changes. So there can be a false positive values. And direct measurement is, as it says, you can directly measure the glucose levels in the blood or in the tissue. There are two types of techniques. First one is a Raman spectroscopy, which I will explain today. And second one is a NIR absorption spectroscopy. People actually started using NIR absorption spectroscopy earlier than Raman spectroscopy. So NIR absorption spectroscopy, since it's an absorption technique, the signal itself is big and it can be implemented as a miniature low-cost device. And it was working extremely well in the laboratory condition. But the issue is the NIR signals are heavily affected by the water, since glucose peaks are very close to water. And when you are applying the technique in vivo, when you think of human body, water is 70% of the total body weight. So you have a lot of water in the body. So applying NIR absorption technique to in vivo condition has been very challenging. Also, NIR spectroscopy is also affected by the temperature. So water and temperature, those are two main barriers to apply the technique for the in vivo measurement. On the other hand, Raman spectroscopy is very specific. You don't have much overlap from the surrounding signals. But the issue of Raman spectroscopy is the signal itself is extremely small. So it is difficult to catch the small signal. Due to the reason, Raman spectroscopy has been considered as mostly as a laboratory technique. But more recently, as the laser, optical device, filters, and detector technologies are improving, Raman spectroscopy is becoming cheaper than before and more sensitive than before. Briefly introducing Raman spectroscopy, So if you are, for example, if you are shining green laser pointer to the wall, then what you see is a green spot from the wall. It's natural. But if you are wearing a glasses made of filter can reject the green light, the excitation light, then what you see is actually shifted color, mostly to the longer wavelength. So you see red color, orange color, or yellow color out of the wall when you are shining with a green laser. If you are analyzing the shifted color, the intensity and color, then you can actually analyze the chemical composition of the materials, which can be either wall materials or paint materials. So this is Raman spectroscopy. So our laboratory started working on non-invasive glucose monitoring using Raman spectroscopy about more than 25 years ago. So initially, we were trying to measure the glucose concentration from the aqua solution. People are mixing glucose. Even though we are mostly focusing on glucose, this method can be applied to other blood analytes, such as lactate or creatinine. So we could actually measure Raman signal from aqua solution with about 1.2 millimolar concentrations. For glucose, 1 millimolar concentration corresponds to roughly 18 milligram per deciliter. So this is slightly higher than 20 milligram per deciliter concentrations. And these are the signals of glucose, lactate, and creatinine, which does not have much overlap with water or other surrounding materials. So encouraged by this result, we applied the same technique for the whole blood analysis. So from whole blood, since the blood itself is very turbid, first set of experiment was done with the whole blood, and second set of the experiment was done with the blood serum after removing the red blood cell and other floating materials. So what we found was that from the serum measurement, we could actually see the linearity between the reference blood glucose concentration and also between the reference glucose concentration and predicted glucose value. So we could measure glucose, cholesterol, or other lipid components, albumin, with a decent accuracy. But when we are applying the technique to the whole blood, because of the turbidity, we could not get a good accuracy. That was the issue. So coming back to the laboratory, the issue of Raman spectroscopy has been always the thing that the signal itself is too small. So instead of using high NA objective lens, this time we were using paraboloidal mirror. By using paraboloidal mirror, we could actually increase the system throughput by 4 times. And with this improved high throughput system, we could measure glucose, urea, cholesterol, or other analytes from the whole blood. And we use the partial least squares calibration algorithms. And this is the regression vector, and this is the glucose concentration, the reference glucose signal from the glucose solution. You can see our PLS model is predicting the glucose changes. Around that time, we were working with Bayer Healthcare. And since we could measure the glucose concentration from the whole blood, then next step was applying the technique to the animal experiment. So we performed glucose clamping experiment. The beagle dog was sleeping, and we connected 2 lines to the animal. One is dextrose, and the other was insulin. So by controlling the flow rate of insulin and dextrose, we could modulate the blood glucose levels of the animal as we want. So this red color is showing our modulated value, and this this blue curve is showing our predicted value. As you can see, our prediction is following the reference blood glucose concentration very well. And similarly, as the previous experiment, we were using paraboloidal mirror and also fiber bundle with a lot of fibers inside of the one fiber bundle. And these fiber bundles are linearly aligned to the imaging spectrograph. Then we performed our first human volunteer study. So volunteers were recruited in the MIT Clinical Research Center. So those were mostly healthy volunteers in between 20 to 40 years old. And they didn't eat any food overnight. And after they come to the clinic very early in the morning, we give them the glucose drink. It contains 75 grams of sugar. After drinking the glucose drink, then their glucose levels are going up and down. And it takes about 2 to 3 hours, depending on the individuals. And during that time, we were continuously measuring reference blood glucose value using the analytical instrument. And also we were continuously measuring Raman signal from the skin. We measured it from the forearm, similarly using the paraboloidal mirror. And this is the result of the first human volunteer study. This chart is called as a clock error grid. X-axis is a reference blood glucose concentrations. These are the values from the fingerstick device. And y-axis is a predicted value. These are the values from our own Raman-based sensor. If our device is monitoring, if our device can predict the blood glucose concentrations ideally, then the dots should be aligned along y equals x. Since it's a real device, there is a deviation along this line. So depending on how much deviation you have from the y equals x line, it can be approved as a blood glucose monitoring device by FDA. So here we were using A30 nanometer diode laser, and our illumination power was 300 milliwatt, and our integration was 3 minutes. So 830 nanometer is NIR. So typically you don't see the light, but 300 milliwatt and 3 minutes integration is still a lot of power. Even though we don't see much adverse effect, but still many people don't feel comfortable when people are saying 300 milliwatt power will be illuminated to your skin during 3 minutes integration time. So we further improved the throughput of the system. This time, instead of a paraboloidal mirror, we used the compound hyperbolic concentrator and compound parabolic concentrator. When the scattered light is coming out of the skin, then they are spreading all over the 2pi solid angle. But even though we are trying to collect a lot of scattered light, maximum we can collect is about 20 to 30% using high NA mirror. If you are using paraboloidal mirror, then you can collect a little more, but not too much. The compound hyperbolic concentrator, what it does is it converts 2pi solid angle rays into the acceptable angle of the collection fiber, which means that you can effectively collect all the rays from 2pi solid angle. By using this small, like non-emitting optical element, we were expecting it will have 7 times more signal from the simulation, but it is a real device. So after fabricating, we confirmed that it can still increase the system throughput by 5.5 times. Using this device, we could reduce the illumination power to 100 milliwatt, and also we could reduce the integration time to 1 minute. So these are the clock error grid and reference blood glucose concentration and predicted value. So they are mostly in the linear region. And it has a similar accuracy, about 17 milligram per deciliter, with 1/3 of the power. Here it's 100 milliwatt, and 1/3 of the integration time, 1 minute integration. Other than that, we were developing a lot of the numerical analysis algorithms to further improve the prediction. still you don't see the Raman-based glucose sensor in the market. There are reasons. So first of all, from the low spectrum itself, you cannot see the blood glucose concentration. So what we showed maximum was the similarity between the regression vector and blood glucose reference spectrum. They look similar, but depending on person, some people think these are not similar enough. And also there was no prospective prediction. So far, our calibration algorithms were using many points in between and predicting the points in between. So these are not the prediction people are expecting for the real device. It should be like this. You can have a calibration period, but after completing calibration period, you should be able to predict the blood glucose concentration without further calibration. These are the two issues. And more recently, we were trying to solve this issue by searching for the real glucose signal from the low spectrum. So since we don't have much time, I can jump this. So what we did was that we developed a new geometry. So these are free space excitation. Instead of using hyperbolic concentrator, we were using oblique illumination of the laser light to the tissue spot and vertical collection. And we did a similar glucose clamping experiment with this time with pig, because pig skin is similar to human skin. So pig was sleeping, and similar to the previous dog experiment, we connected two lines, one dextrose and the other insulin. By controlling flow rate of these two, we could modulate the blood glucose concentration of the pig. But this time, we were modulating the blood glucose concentration up to very high level, because our goal is actually to measure the blood glucose concentration from the low spectrum. So these are the modulating level. So it's starting from about 50 milligram per deciliter, but we were modulating up to 800 milligram per deciliter. And as a reference measurement, we were using two devices. One is a YSI unit. That's a clinical gold standard. You need about few milliliter of the blood. And also as a second reference method, we were using fingerstick device. And this experiment was performed during 7 hours, and Raman measurements was taken every 5 minutes, and blood draw was also taken every 5 minutes. We were illuminating the tissue with a 250 milliwatt and integrating for 5 minutes. So these are the signals. So these dotted lines are Raman spectrum from the reference glucose solution, and the upper spectra, they are from the real tissue spectrum. As you can see, they look very similar to the glucose concentrations. So what we did was these are different spectrum. So our assumption was that during the modulation, if you are, for example, if you are selecting two spectrum from here and here, by subtracting these two spectrum, most of the spectrum changes are coming from the glucose level changes, since assuming other solid components such as fat, collagen, proteins are still staying the same. So these are the different spectrum. So these blue lines are from the difference, the blood glucose level difference was about 250 milligram per deciliter. And this red curve, they are coming from 450 milligram per deciliter. As you have a more blood glucose level difference, then the signal intensities are growing. And by following this 1125 glucose characteristic peak, you can actually draw a linearity between the delta blood glucose concentration and intensity at 1125. These are the strongest signal from the glucose spectrum. And using this scheme, we can simply predict the blood glucose concentrations with a prospective prediction. And this first analysis method is utilizing different spectrum, but we can also predict the blood glucose levels using single spectrum. So this second analysis method, we were calculating the ratio between the blood glucose concentration from 1125 and the strongest Raman signal from the solid components of the tissue. The advantage of this method is that when you are taking blood glucose levels at the same point, then you can reliably predict the blood glucose concentration using the previous method. But during the 7-hour experiment, sometimes animals are moving, shaking, which means that your measurement spot is moving to the nearby spot. If the measurement spot is moving, the issue is that then you are shining slightly different spot, for example, 1 to 2 millimeters different from the initial spot. Then the issue is that you have another level of the autofluorescence signal from especially from the melanin. As time goes on, it will be bleached, but if you are using same analysis method, you will be in trouble. But if you are normalizing your glucose signal to the solid components of the tissue at the same spot, regardless of the sensor stability, you can still predict the blood glucose concentration. This second graph is showing the linearity between the blood glucose concentration and the ratio between the glucose Raman spectrum to the solid components of the tissue. And after the measurement, we were inspecting the tissue site. These are actually the small center part of the ear tissue is where we were taking the measurement. And from the histology image, we confirmed that there is no damage to the tissue. So what we did was that we could actually observe the blood glucose spectrum from the skin, and also using this strong low spectrum, we can do the prospective prediction. So these two issues are solved, but still there are remaining issues. So our measurement were modulating the blood glucose concentration up to 800 milligram per deciliter, which is extremely high. Human usually do not go there. Human range is typically between 50 to 300 milligram per deciliter. So whether this method can be applicable to the physiological range of the blood glucose level. Also, second issue is that our current device is, although I call it device, it's more like an instrument, and it is quite expensive and bulky. And where we are standing compared to other commercially available sensors, for example, finger stick device or minimally invasive sensors. So these are what we are currently working on. So as a conclusion, what we did was that we could measure the glucose signal from the in vivo skin. And using this direct observation of the glucose signal, we could predict the glucose value without complicated calculation. But our challenge will be maintaining the accuracy. Our current accuracy levels are okay. Our MAD values are about 10%. So it is similar to, so currently our performance is, our accuracy is between finger stick device and minimally invasive sensor. So we are slightly worse than the finger stick device, but our prediction values are more accurate than the minimally invasive sensors, but we are bulky. So maintaining the accuracy while we are still miniaturizing the device will be a big challenge. Yeah, this is the end of the presentation. Thank you. Let me know if you have any questions.
Yeah, thank you, John. We have a couple of questions from the participants. Am I audible?
Yep.
Yeah. So what are the challenges in developing a miniaturized, a portable version?
Mm-hmm. Yeah, so currently our device is bulky. It is mainly because of we are using scientific grade instrument. Raman spectroscopy signals are small. As a result, we are using very sensitive detector, and also we are using high throughput instrument. So as we are miniaturizing the system, for example, the current camera is like this big. It can become small as a cell phone detector, cell phone camera. But whether it will maintaining the signal and signal to noise ratio is a big question. But this can be also solved when there is a mass production of the device. For example, when I was like a graduate student, I was using one of the first version of the digital CCD. It was 1,000 by 1,000 pixels and 8-bit grayscale. Nowadays, nobody is using it, but I remember I paid more than $10,000 for that. So as time goes on, detector technologies, especially if, for example, if big electronics companies are coming into the field and start producing a lot of detectors, then it can go down. Yeah.
And can it be integrated with the other vital meters, like the one which is used for measuring blood pressure? Can we integrate this with those devices?
Yep. So I think it can be integrated there, but technology-wise, probably glucose sensors are more expensive and slightly bulky. So other sensors can come into, for example, you can measure blood pressure or like a blood oxygenation or other temperature sensors can be integrated to here.
So that it can be more cost effective also.
Yep. And also, although we were mostly focusing on glucose monitoring, it can also monitor other blood analytes such as urea, lactate, or creatinine, which means that you can also monitor what is happening to the athlete during the sports. That kind of monitoring can be possible.
Yeah, thank you.
Thank you.
So once again, thank you, Dr. John, for this nice presentation. And thank you once again for accepting our invitation. Thank you very much. Have a nice day.
Thank you for inviting.
Thank you. Yeah, my pleasure. Can this invitation?
So we request all the participants to use the same link to join for the next session at 8:15. Sorry.
After 10 minutes. Thank you.